OK，那上礼拜没来的，上礼拜就是讲一点那个修尔算法 s h o r s algorithm，就是教科书第5章的所有内容。那讲比第5章还多了，但是我们今天就那个讲完之后，我们就讲第6章的，就是第二个大 type 的这个叫做 Grover's algorithm。那如果你从来没有听过这个，第一次听会觉得很神奇。那就会让你觉得这个东西非常神奇。那上一个修饰 algorithm 它的概念主要是说，它是在对付一些具有非常多代数结构的东西。那 in particular 就是说像数论相关的，刚好这个分解这个合数这件事情刚好是修饰 algorithm。那还有我上次来介绍就是说，你可以把它想象成是一个抽象的 RBDN group，那你能够找到它的 subgroup，所以它本身是一个群论比较 group theory 的群论相关的这种问题。那 Borrowing algorithm 就是算是more general，就是它要对付的问题是比较没有代数结构。OK，诶，那就是95年是修饰 algorithm 出来，那94年其实就有这个 Borrowing algorithm，那这两个算是quantum algorithm 当中就量子算法里面最大的2只。那我想大家可能有一点感觉，就是说我们目前学到的这些量子算法。比如说像是夺取纠察，它的假设是问 F 是 constant of balance，那 first running 是说有一个 secret S，那 Simon's algorithm 不知道大家有没有讲，就是说也是 T 跟 subgroup 的特例，就是说，如果 f of x 等于 f of y，if and only 这个 x 叫做 y 加 s，那你要找到这个 s。那 factoring 就是一个，那第4个就是分解合数嘛。假如它就是你可以把它视为是一个有限阿贝的 finite abelian group 的一个 subgroup。所以这些呢，目前我们面临到这两种算法，它是可以说是有很多复杂的代数结构在里面。OK，那问题就是说，那假设今天我们要讨论的问题是你的问题更 general，它没有代数结构，那更一般的是它没有群论的这个代数结构，没有阿贝尔群的这个代数结构。OK。那什么叫做没有代数结构呢？比方说，第一个问题就是 unconstructed search，我给你一个方程 f，然后我希望你找到一个 x 值的 f of x 等于1，或者你告诉我其实没有这个 x，所以这个很 general。这个问题是没有你不知道 f 的任何结构。我问 f 有没有一个 x 值的 f of x 等于1，这个 f 不一定是从群论来的，也不一定是从分解正整数来，它没有任何明显的代数结构。OK，or wait. So the second example is for the collision. Collision is that I give you some f, and I told you that f is 2 to 1. Uh, and I want you to find x and y, x different from y, such that fx equals to fy. So this collision meaning that you need to find a pair. So notice this is different from Simon's problem. Simon's problem has additional conditions say that if they are the same, then they're a secret S. But collision is a more general case. There's no particular S. Or so-called element distinctness. I give you F. You need to tell me this F is one-to-one function or infinity. So this is like very general problem. Looks much difficult than previous. Or so-called counting fact. How many X such that F of X equals to 1? Or so-called parity. I give you a function F and tell me that what's the parity of F. So you sum over F and modulo 2. Okay, so my question in this lecture is telling you that is there we need to answer this question. Is there going to be up or there? Okay, so let's work on the first one called unconstructed search. I give you f and find x such that f equals to 1, or tell me there's no or if there's no such x, and you need to tell me. Okay, so classically you can prove that there's nothing you can do, right? You just check one by one. So classical lower bound is just capital A, just the number of possible x. Because you need to do x one by one, because you don't know any information of f, right? There's no mathematical structure of f. Oh, okay. So the main results for this lecture is for Grover's algorithm. My claim is that there exists a quantum algorithm which speed up only takes the square root of n. Okay, so if I mean if this is the first time you see this algorithm, this looks very weird because this means that suppose this f there's a single x such that f of x equals to 1. The goal is to find x. Possible x has n choices. The class there is a quantum algorithm indeed take the square root of n. Okay, so this is really weird if you think about it. Okay, I mean this is pretty weird. So this means that if you have possible n choices, capital N choices, if you want to find x such that f of x equals to 1, then somehow like you don't need to take you don't need to look x one by one, but you only take the square root of n. Okay, so it's quite amazing that imagine you have a box, right, containing like 10,000 volts, and one white and the rest are black. So practically, how many times would you need to check which volt is let's say white? So in the worst case, right, 10,000 times because you or in average about 5,000 because you need to do like one by one. But for a quantum that you only take a square root of n, so you only need like 100 times. So it's like there's an algorithm around 10,000, but if you do quantum, you only need like 100 times to find x. Okay, so now we are going to talk about detail. So for Grover's algorithm. Okay, so we're doing some mathematics, right? So let's suppose that there's a this x0, which is the solution, and I give you oracle such that this oracle will detect the solution. So so the mathematics what I write is you apply on the x will give you extra phase as a -1 fx f over x. Right? This is the standard quantum or the oracle setting. And the question is that there exists weird particular x0 such that when you plug x0, there's an additional minus sign. The rest are the same. Okay, the goal is to find x0. Is it clear? There's a secret x0, right? When you have applied x0, there's an extra minus sign, and the rest are the same. The goal for you is to find x0. Okay, so I mean we know that at the beginning, right, we can create all the superposition of x, but x0 is very small. The probability that you measure x0 is 1 over 2 to the n, right? So so probability of appearing just as low as others. Right, this is what right, say you start with all 0 and then purely you use and how to find all superposition, right? And then if you take UF, you get this. But for the correct answer is x0, there's a minus sign, but the rest are positive sign. But when you measure that, the probability you measure x is always 1 to the 1 over 2 to the n. So it looks there's no yeah. Okay. So the idea is that maybe we can do some rotations, right? Let's say I start with all the superposition. There's a extra minus sign, right? I do some rotation, and after a lot of rotation, then I get x0. So if this idea works, then I can get x0. Okay, good. So maybe I draw this picture. All right. So let's say I define a vector t, which is the vector which is does not contain solution. So this is sum over x divided by 0x. So this vector t is also equal to x0, right? Because there's no x0 component here. So if you draw it on the draw this on two-dimensional vector. This is x0. This is t. And then your original state, right? Your original state size is a superposition of x0 and t. But we can calculate this table, right? Let's say we calculate this t, the product with this side with this t. Okay, so obviously that t and psi has very large overlap, right? Because only one of x0 comes here, but there's a 2 to the n minus 1. So the cosine of t psi is 1 over square root of 2 to the n times 2 to the minus 1. Okay, and the length of t is square root of 2 to the n minus 1. So you can see that so you can say this number is very, very close to 1. Okay, so this number is let me write it obvious. Okay. So this cosine theta is merely just 1 minus 2. So this is very close to 1, right? And it's large enough. It is very close to 1. So that means that this angle is extremely small. So the goal for me is to find some location such that this state becomes this. Once it rotates become this, then I measure it and I get the range. But now it's at the beginning it's very small. It has a very small angle. Okay, so this is the idea. Okay, so so before we do this rotation, let us see some simple the first rotation. Okay, so the first rotation is the UF, right? So remember that if my space represents ax0 plus bt, when I apply UF, right? X for the correct answer, there's the extra minus sign. For the t, there's no change, right? So if your vector looks like this t and x0, when you apply this UF, you get extra minus sign on the x0, the component coefficient, right? So you will get vector like this. Because the first this a will become minus a. Right. So for x0, then you get extra minus sign, right? So, but angle is the same. Okay. So this is the first thing you need to remember when you do a UF. Then for t there's no change, but for x0, basically you just do the mean value. Okay. Good. Alright, but now we have a problem, right? Because if I apply UF twice, then I get back. If I apply UF squared, then I get back, right? So you see that hard to make these states like approach x0. Okay, but we have like other operation, right? Particularly this Hardeman. Okay, so okay, so now I can create another unitary. Let's call this unitary u sub 0. Okay. So this unitary sub 0, then I can create because I know what it takes, right? It's very simple. When this u0 apply on 0, then it becomes the same. Otherwise, there's an extra minus sign. So I can create this as a rotation because I know what. I mean, I know which one is the 0 string, so I can create this unitary. Okay, so my question is that how about I apply this hn u u0n and okay. So let's see the operation. So let's say I apply this to this a x0 plus bt. Okay, so for convenience, let me just choose another vector called h, which is an auto superposition of x. Suppose this guy apply on the vector spanned by h and its complement, let's say h prime. So let's say this guy apply on a prime h plus b prime h prime. Okay, so this original Hardeman apply on all superposition becomes zeros, right? Because remember that Hardeman apply on 0 will give you all the superposition. But Hardeman is a unitary, right? So if you apply a square, then you get back to send back. So Hardeman apply on all the superposition will back to 0. Okay, and for the second one, then you just write. Okay, so now constant fit. Okay, so when this u0n apply on 0 becomes the same. Okay, so this is the same. And for the second one, then let me just write it. Okay, so my claim is that this guy, this u0n, so this should be So this should be false. This should be false. But when another argument applies, there will be another minus. So let me just write that. Okay, so we have a right. I will provide a proof. So this here. Okay, so this is the term. This is the term that then we want to compute. Okay, so we're gonna do it. So when Hadamard apply, sorry, when this U 0 n apply on all 0, it becomes same. So I get the same guy. Right, and then there is the second one. Second one is where? So we got it. Okay. So my claim is that my claim is this guy is exactly minus 1. Right. All right. So my claim is that this guy is minus. Okay. So why this is the case? So notice that when Hn apply on each part, this guy can be expanded into the standard basis. But there's no 0 n in this expansion. So let me just write. Right here. So my claim is that if you have this, if you do this, there's no. You can expand it in terms of different bases. You can expand it with finish different bases. But this alpha 0 n must be 0. So my claim is that this is true. Okay. The reason is that otherwise that let's see. Okay. So the reason is that I know that these guys is this H prime, this H and H prime, by definition they are 0. Okay, so right, so this is 0. So I can just write this guy in terms of 0 n and Hadamard n, Hadamard n H prime. This is 0. This is 0. Because Hadamard square is identity, so I get H. So for this guy, I get 0 n, and this guy is this x alpha x. So this is alpha 0. Okay, so this means that there's no 0 all 0 component in Hadamard apply on H prime. So when you apply this U0 to n, there's extra minus sign because every vector is flipped. Okay, so result basically is A prime and H minus B prime H prime. Okay, so this is the result. So maybe it's just this one. Oh, maybe it's harder. You forget about proof, but let me just using this problem. So this plot is obvious. So this means that when you write your original vector as a span of H and H prime for H. So remember H is always superposition and H prime is also local component. When you apply this and apply this new rotation, then you will flip H prime. So so this is all superposition. If you have a vector in terms of H and H prime, when you apply this new rotation, this will flip this guy. Will flip this guy to minus H prime. Okay, when you apply this Hadamard to the n and U0 n and Hadamard. Okay, so now if you remember these two rotations, then And let's call this rotation F. Okay, so now everything looks simple, right? So you start with O0, where your original state is this or superposition. When you apply this U, then you get extra minus sign flip. You need a you get a zero along the axis of t, so you get U as side here. So it becomes that picture. And then when you apply F again, right? When you apply F again, so remember this vector, right? When you apply F again, you will flip along this just orthogonal to this H. So you get a vector here. You get a vector. And the angle, you can see now this F, UF, this angle along this T is 3 theta. So originally this is theta, but now it becomes 3 theta. So at the beginning, that the angle with T theta after applying F and U then becomes 3 theta. Okay. And you can do it again, right? Now you have this, you have with 3 theta, right? You can apply UF. When you apply UF, then this vector just 0 along T. So you get this vector, which is 3 theta. You apply UF, F, UF. Now if you apply again, you apply this F again, then you reflect along this H, right? So it becomes this guy. Become 5 theta here. Right. 4 theta here. So total angle with this T is 5 theta. So if you apply FU, then you get 5 theta. Okay, so now you can see a trick, right? If I keep using this sequence of U and F, then this angle will grow. That's how with theta is 3 theta. If I apply again 5 theta, 7 theta. So my question is that how many times I need to do to make this angle to be along perpendicular to x now, x0. This is very simple, right? Just pi over 2. So how many times for me to keep using the consecutive FU? After k steps, the total angle will be 2k plus 1 theta, right? Because I start with theta, 3 theta, 5 theta, so after k step is 2k plus 1 theta, and it should be pi over 2. So then you match the load back. So let's say if theta is very small, I forget about this one, right? So k is approximately pi over 4 theta divided by theta. So what's theta? So remember the original I write the cosine theta is this guy, 1 over 1 square root of 1 minus 1 divided by 2 theta. Okay, so now I can use this to get a theta and I get the results, right? So first that suppose n is very large. So if cosine is 1 square root of 1 over 1 minus 2 to the n, then sine theta is 1 square root of 1 over 2 to the n. And then when theta is very small, the sine is approximating theta. This is like calculus. High school. So theta is approximating sine theta is 1 over square root of the n. Okay, so finish. So k is approximately pi divided by 4 theta. Theta is 1 over square root of n to the n, right? And the pi over 4 is less than 1. So now it's less than square root of n. Okay, so why I have done is that I showed there is a quantum algorithm which can find the x0, can make original vector rotate to x0, and when you measure it, you get x0. So this is amazing that you only spend like square root of 2 to the n, which is square root of all the possible solutions, but you still get the answer. So this is somehow like this power of quantum algorithm. So we don't just loop the answer one by one, right? We create a superposition and we do rotation such that we make the correct answer have the largest angle. Okay, so this square root of this is Grover's algorithm. Okay, so circuit. Okay, so previous just the proof, but we can do that in circuit. So remember, circuit is very simple. We start with all the superposition, and then we apply the consecutive this F and U. So in the textbook, we call this operator quadrants. So we call this operator G. So we start with all the superposition and apply consecutive G. And once we take the order of square root of n different G's, then we get the answer. Good. Okay, so this is the proof. And remember that so this G is composed with U for the original oracle and the algebra conjugated by this U0 to n. So this is consecutive F and the consecutive U and F, U and F, and once you apply square root n times, then your results will be very close to the answer. Okay, so good. So this is the first result that if you have n different choices and there's only one answer, then you can take a square root of n to find that answer. Okay, so my question for second one is that how about suppose there are n different solutions, not just one. The previous algorithms is that suppose I have one solution, I only have one solution. Now I can take a square root of possible solution and I get an answer. So suppose there are n different solutions, and you know there are n solutions, then how many times that you need to do this rotation? Okay, so the proof is very simple, right? You just go back to the original proof, and you just modify this data. Because if you have a lot of solution, and this theta angle will be large. So technically, let's say I could write S to be all the states, all the linear, all the equally superposition of the answer of the correct answer state. So I sum over all the vector x, and f of x equals to 1. And this t is the same previous one. And the u is the summation, the sum over s and t. So I can calculate in size data as what I did, right? Previous what I did. So if you go back to this equation, if you have one solution, this will be 1. If you only have n solutions, you just replace this 1 by n. Right? Proof is the same. So your sign will be m divided by 2 to the n or m divided by capital N. Okay, so very simple. You have sine theta, which is the square root of m divided by n. So basically, you can just rotate this. You can just rotate pi divided by 4 divided by square root of n divided by n. Alright, so conclusion. Conclusion is that if you have n marked item or n answer and n inputs, Power's algorithm can find a marked item in n most square root of n divided, which is better than original classical algorithm. Better than square roots, quadratic improvement of all these classical algorithms by taking the square roots. And if the number of solutions is larger than 1, then you get some extra factor. Okay. So these are thousands of papers. You can check there are thousands of papers, different applications on this Power's algorithm. Because somehow like this Power algorithm can take you to brute force search. If you have some algorithms, then you finally use some classical algorithms, and you want to do some brute force search. So originally, suppose you only have you take n different searches, but now you just take a square roots, right? So it's very powerful. It seems like you can apply to any algorithms. You take any classical algorithm, whatever it has a brute force search, then you can make it square roots better. Okay, so for example, anything you need to brute force search for 100 times, then reduce to 10,000 times to 100 times. Okay, so square root of n divided by m. Okay, so my question for the third one is that, but what to do if we don't know how many solutions are there? Right, this is the third question. So the results basically what I say is, if I have n different possible answer and there are n solutions, then I can take a square root of n divided by n. I just do this rotation, then I make sure that I get one solution. But my question is that maybe in some case that you don't know how many answers. So you don't know n. So what do you do? Because if you don't know n, maybe there's only one, right? So you take the square root of n. If there are a lot of solutions, but you don't know, you think, oh, there's only one solution, then you will rotate, you will do more rotations. Okay, so but if you do more rotations than you should expect, then you will become there, right? Then you will not fit into this case. So if you have more solutions than you expect, then if you run this algorithm, you will fail, right? Because this vector will not conduct this x0, but just go this direction. So my question is that, oh, suppose I don't know how many solutions, then what can I do? 这我要讲的刘总，就是说这个 derive 算法是说，如果你有 m 个 solution 的话，那么你有 n 个选择的话，那你只要花开根号的 n 除以 n。那如果说我现在问题是说，那假设你不知道有多少个答案，你就不知道这 m 是多少，那你就不知道要找多少。Okay, so this is the question. Alright, so the answer is very simple. So let's say suppose that I imagine running this power algorithm for variable for different locations. Let's say I rotate y is 25 and these different locations. And I plot the amplitudes of this answer state. So I plot the probability that I get this. Okay. So obviously that this answer states, right? This answer states. Somehow like the probability you measure get this one is a sine theta of this angle. So the sine theta of this is pi over 2 cosine theta of this. So it's basically sine theta. So the probability that you measure the correct answer will be sine squared. And we know that so sine is what? Sine is a periodic function. Sine is a periodic. So in particular, if let's say if you have one solution, then you will see that this function, this sine squared, has a period which is pi square root of n. The idea is that why? Because I know that if I rotate pi divided by 4 square root of n, then I get this. Right? If I rotate it 4 times, then I go back to this. So there's a period which is 4 times pi times square root. Because if I rotate pi over 4 square root of n, then I get this one. But if I rotate 4 times, then I get back to the original one, right? So there's a period. So this period is a function of n, right? If I have no solution, then if I have only one solution, the period is large. If I have a lot of solutions, then period will be small. So obviously that okay. So this guy will oscillate with period pi square root n divided by n if you have n solutions. So now we can what? So what we have a function which there's a period, but I don't know the period. This is exactly period finding, as the same as Schur's algorithm, right? Because I have a period. The number of solutions n will affect my period, but I don't know the period. Okay, so I can run Schur's algorithm. So the idea is that I run Schur's algorithm, and Schur's algorithm will give me some estimation of period. Then once I get estimation of n, then I can run this algorithm. That's it. Okay, so this is the idea. Okay. And basically this is so-called quantum counting. So we can count, we can use this algorithm, we can use Schur's algorithm composed with this algorithm and get the approximate counting of different solutions. So you just use a quantum Fourier transform what we say in previous lecture and then apply on this algorithm, then you can find you can get an approximation of the answer. There are some details. So so let me just go through this algorithm. So idea, as I say, the problem is that the algorithm works best when you know exactly how many solutions. But let's say suppose you don't know. The idea is that you just run it for a wrong number Okay, so if you don't know, then you run number of different iterations will reduce the success probability. Okay. The idea is that we know that the amplitude of solution state oscillation with this type function. So there's a period. So the goal is to find a period. So we don't need to know exactly the number of solutions. We just need to do the approximation. Or we just need to approximate to a close number, then you repeat the algorithm for constant time. Then you can check that you can get it correct. So idea is that how do I measure, how do I get an exact correct or the estimate the correct? Maybe and use okay. So idea is that we just use the quantum Fourier transform, right? As the previous I said, you can use a quantum Fourier transform as a subroutine of Show's algorithm. Okay. So hopefully you can remember this version. So the algorithm that I will prepare the register and run this algorithm for many times. By quantum Fourier transform, then I can get a period that actually escalation period that I get possible approximately. Okay, so remember this is the remember when we do the so-called quantum phase estimation, these are control unit. But now it's a control problem, right? Because problems we need to run these problems out. And do the Fourier transform. There are some detail, okay? But simply speaking, this is the idea. So idea is that you try to do a rotation, right? But since you don't need to get the correct, so you can assume assume m is power of 2. Maybe some 2 to the small m. Okay, so now all you need to do is you just do the so-called similar to binary search. Okay, you first only rotate. You first only rotate so you first only rotate twice, and if you don't find an answer, then you rotate 4 times. If you don't find an answer, you rotate 8 times. Just keep doing using using a power of 3. Okay. So you rotate 8 divided by 2, 8 divided by 4, 8 divided by 8, 8 divided by 2. Now until you get a log item. So this algorithm takes a small m, which is log n divided by n steps, and the total number of the total possible steps is 2 to n divided by 2. And if algorithm equals 1, and then put the n square root. So you can see that the largest term here in this contribution is the square root of n divided by n. And the thing is a geometrical series, right? So if you take a geometrical series and you start with largest term, then the rest will the rest the total sequences at most 2 times the initial one. So maybe you don't know what I'm saying. So this is a simple fact. If you start with this any geometrical series and such that the ratio is half, then the total sum will be less than basically very simple. Start with a0 and a0 divided by 2. And whatever a0 divided by 4, up to some terms, and this is at most 2 and 0. Very trivial because if you sum infinite times, then there is some infinite terms is 2 and 0. So this guy will less than this. So these terms is at most 2 times the largest, which is square root of n divided by n. And then extra 2, then I'm sorry to this big O of it. So this is the proof. One up. Alright, so conclusion. If I know there's only one solution, then I need a square root of n. If I know there's m solutions, then I need a square root of n divided by n. If I don't know the number of solutions, then I need O. I still get a set. As the second one, I need the O of square root of n divided by n. But let's say, what if there's no solution? So if there's no solutions, right, then whatever times that you rotate, there's no way you get anything. There's no way you get anything. But if this is the case, then if you run the third algorithm to check how many solutions of n, then you'll get 0. you'll get approximate 0. So that means that at most, you still need you just need an O of square root of n times, and you know there's no solution. Because if you run this, you run this algorithm, then you measure something. But if you measure it, you plug into original f, and you say, why this f is still 0, then you know there's no solution. So you can check this. You can check. It's similar to the previous question. The Simon's algorithm. You can check the answer, right? So if you run this algorithm and you measure something, and you just plug whatever you measure into original function f, and you get nothing, you know there's no solutions. Okay, so this is Squabbers. Okay, so if you forget about everything, then this is the thing you need to remember. It's a cheat sheet. You don't need to know it. If you forget about the algorithms, there's a result. Okay, so let me say again. 这个我再讲一个事情，就是说这个算法就是这样。如果你全部忘了也没关系，这个意思就是说呢，你有一个盒子，这个盒子里面有 n 个东西，然后有 n 个是正确答案的话，你只要用开根号的 n 除以 n， 你就可以得到答案。它的特点在于说，它比古典电脑多一个开根号。讲了。Okay. So if you have basically if I have n different possible solutions, I have n different choices, but there are m solutions, I only need a big O of square root n divided by n, I can find the one answer. Okay, so good. So now let's talk about applications. 我现在讲一些比较神奇的事情，就是找到所有的 solution， 然后所有 solution 就没办法，你就要一个一个去看。因为你可能会漏掉一个，因为每次找的可能是一样的，之前找过的。哦，对，所以这个算法只能找到一个solution。那如果一定要找到其他的话，你就要一个一个再找。然后一定要找到全部的话，那就没有加速，你就全部把东西一定要看完，因为你会漏掉最后一个。OK， 这个算法比较神奇是，如果你只能找一个，找其中一个。那等一下我讲这个。不同 example 就会，我讲一个 application， 大家没有听过就会觉得很奇怪，所以这个 example 会给大家告诉说这个 Squabbers algorithm 有非常神奇的地方。OK, so applications， 我讲这个问题 ，this is called collision problems。这个问题比如说this is that I give you a function， and I say this function is 2 to 1。2 to 1就是说两个不同的 x，there exists x and y such that f(x) equals to y。And the goal for you is to find a pair. To find a different x and y such that f of x equals to f(y)。就是你有个 function 啊，它是2对1的，那你要找到它的 partner， you want to find collision， 你要找到它的 partner， 找到 x 跟 y 不一样时，它们 map 是一样。OK， this is and classically you can prove this is okay. So I will recall through this is called the first-order paradox. So what this idea is that you only need a square root of n time, then you can get an answer. 那这个概念就像说，你可能听过那个什么23个人在一个教室里面，就有超过1/2的几率2个人会是同一天生日。那这个问题这个结果比较奇怪，是因为生日看起来有很多，对不对？365天应该不容易重复，可是为什么23个人在同一个教室里面就有很高的几率呢？有2个人会生日呢？对，这是这个结果。So this is a classical lower bound. So let me just recall the proof. And this is usually called the first-order paradox. If you're a class with 22 people and you have probability greater than half, then at least to share the same version. Why? So my idea, can you prove this? Okay, so to prove this, we need a so-called generalized birthday problem. Suppose there are m different possible birthday, right? And you collect k people in this room. So I want to ask, what's the probability that there's no collision? And this is a high school problem. So let's say, so my assumption is that each person can choose birthday uniformly and random and independent. 就是我现在要说教室，如果有 n 生日有 n 个不同的可能，那我在教室凑 k 个人的话，那这 k 个人都是不一样生日的几率是多少 ？OK， very simple。我的问题是这 k 个人生日都不一样，这个简单的数学问题。Alright, so the first one, the first reason, So let's say the first person, right？就第一个人他生日随便乱选。Probability that the second guy is different from first guy is m minus one divided by。因为第二个人可以选生日，但第二个人只要不要跟第一个人重复，要是两个加无就不一样，所以就一减掉一除 OK。And similarly, if there is a third person, then third person should be different from the first two, right? So it's m divided by m minus 2 divided by m. So 1 minus 2 divided by m. And let's say the first guy, 第四个人不能跟前三个一样嘛，对不对？所以是 m 减单数 m。OK， 那就非常简单了。第 k 个人呢，the case guy the first day of case guy should be different from all the previous k minus 1. So it's 1 minus k minus 1 divided by m. And since they pick their birthday random, so all k birthday distinct are the product of all these. So just 1 minus 1 divided by n, 1 minus 2 divided by n, 1 minus k minus 1 divided by n. So let's say if m is large, then it's close to 1 minus. So I just take the first term is 1 minus 1 plus 2 plus up to k minus 1 divided by n. So it's 1 minus k times k minus 1 divided by 2n. Okay, so it's approximately if m is large enough. So these are the results that all k birthday are distinct, right? But let's say suppose I want at least one share of the same birthday. Then it will be very simple, right? At least one shared birthday is just 1 minus p of if they are all distinct. Okay, so as I said, that this is just this. So it's just 1 minus this term. So we just k squared divided by 2n, right? So it will be k squared. So if the probability that at least one will be just k squared divided by 2n. And then if I want this number to be large, let's say 99%, then k will just approximate square root of 2n. So square root of all the possible birthday. So that means 所以这是为什么365天嘛？因为365的开根号接近23，其实没有接近，但我说就接近这个量级。Proof. Okay, so what this means is that if I want to find a collision, the algorithm I can pick, I just randomly pick different x and I put in f. And if I take a square root of n different x, then I will get then classically I will get a collision. But how about quantum? How can you use this Guavar's algorithm to make better than square root of n? So for classical, just square root of n to find the collision. Can you do it better using the Guavar's algorithm? 反正没有听过可以听一下这个。OK， 那classically square root of n is the best one, right? How about quantum? So let me just explain this algorithm. So our algorithm is very simple. You first purely k different inputs, and you store f of x in the hash table. 这个 idea 就是说我先随便选 k 个加5，然后把 k 个加5背起来。对，然后放这个写程式就是放在 dictionary 里面，那就是把它背起来，就是放在集合里面。那也就是说我等一下要查新的元素有没有掉在这个集合里面的时候，我只要 constant 时间就好。写程式用集合去写。所以 idea 就是说，你先 purely k different input and store f of x in the hash table。那就我画这个图，就是说全部有 n 个 solution， 我先随便挑 k 个把它丢，随便选 x， 随便选 x different k， k 个 different x， 然后丢进去。那是有可能是说这里面就有两个是重复。那如果是这样，我就省多，等下少3。对 ，so I don't need to. So if this is the case, then it's fine. If there's no collision, then still be fine. Okay, then I use a Guavar's algorithm on the rest n minus k. And I check whether there's a solution matched with k. So notice that if there's no distinct here, then there will be k solutions in the rest of the minus k. 这什么意思？就是说，假设你现在先选 k 个东西嘛，你现在先给 k 个不一样的东西放在旁边，对不对？ 那如果说这个方程是2对1的话，那在剩下来的 n 减 k 的里面，是不是会有 k 个家伙跟原来的那个家伙是 match？对吧？So如果我使用 Gravers algorithm 在剩下的 n 减 k 的东西里面的时候，我就会有 k 个 solution，对吧？讲没有？OK。So if you 你被我说服，if you convinced by me, then what's the total rounding time？那我花多少时间？我先花 k 个时间，来，I apply k different lookup。Now I can run Gravers algorithm. So Gravers algorithm is known as the square root of n, square root of n minus k. 我有 n 减 k 个 solution，but there's a k solution here. n 减 k 个不同可能，然后你有 k 个正确。So total running time is k plus square root of n minus k divided by k. OK，这时候神奇的事发生。If I take k to be cubic roots of n, then this will be cubic root of n. And what about this? So let me just write it down. So for this collision problem, the total time, right? The total time is k plus square root of n minus k divided by k. If I plot k to be n to the 1/3, then this will be n to the 1/3 plus. This is n minus n to the 1/3, right? But n to the 1/3 is much smaller than n. So I can say this is n divided by n to the 1/3. But this is n to the 1/3 and n minus 1 minus 1/3 take the square roots. So this is 2 times n to the 1/3. Right? 因为这个后面再开根号有什么 n 除上 n 的1/3次方，就是 n 的1/3次方，再开个根号就 n 的1/3次方，所以两个 n 的1/3次方加起来是2倍 n 的1/3次方。So this algorithm actually run 2 times n to the 1/3. 那你们就很神奇。Then this is less than n to the square root. 比刚 classical 要找 collision 要开根号，对吧？要 n 的1/2次方嘛。但是我使用这个框的，我把 Gravers algorithm 塞在这个 collision 里面，我只要 n 的1/3次方就可以找到两个方程 match，两个不同的 x match 到。这我们听起来很神奇，你会想一想就会觉得神奇。Okay, so if you run so we just need a runtime of cube roots. So this is the result. OK，那这有一个故事，就是说，其实在1994年那个时候，人们就已经知道这个算法，因为人们很快就已经知道说，在古典电脑里面要找到一个方式，要破解一个 collision function，要开根号 n 的1/2，那光的只叫 n 的1/3。可是就会产生问题，就是说，那你怎么知道有没有更好？说不定这个算法不是对的，可能有 n 的1/5啊，n 的1/6啊，n 的1/8啊。为什么 n 的1/3是对的？那这个问题其实非常困难，就是在那之前，这个问题在21世纪之前，大家是不知道。那经过了很多人的经过了一篇博士论文的努力，可以证明这个是对的。那这是 by Aaronson in 2002 or something。proof 是非常困难。这个证明就是说，你要证明，我们后面会讲到，就是说这个 collision problem 这个证明它是非常困难。但是我们会讲到Gravers 的证明。那如果对这个 collision problem 有兴趣的话，可以去看这个 YouTube 影片，就是 Aaronson 的 collision lower bound after 12 years。然后这有1个多小时，就是讲这个 collision 问题的这个细节这样。如果你想要知道更多，特别这1/3怎么来的话，而这1/3为什么是最好？为什么不是1/5的？好问题。所以你这个2对1的函数是指这 n 大 n 的里面，每一个人有其他的，每一个人刚好有一个他的 pair， 对。哦。那你的问题是要找到两个，找到 pair，任何一个 pair， 对，任何一个 pair 就行。不是全部。但你要找到一个 pair 就很难。你如果要 classical， 你要找到一个 pair 就要 n 的2/3次方，如果 n 是2的100次方找不到，就2/50。它这个是 n 的1/3次，它这个就有差，因为这差别。有点。OK，so 那这只是一个奇怪的应用了。那好，还有其他应用，那我们来讲一下这个，好吧，我们再讲5分钟。那这个我们讲完下一个例子来下课，就是这个
another application is called amplitude amplification。那这个因为等一下要讲另外一个 example 啊会这个需要先抢一下，不然等一下会听不懂那个 example 在说什么。Okay, so what this so now I provide another version of God. The idea is that if I have an algorithm which is successful raising p, then in general I need to do 1 over p times to make it success. Then I need to do 1 over p times to push the success probability close to 1. 那这句话是什么？这句话说，假设你今天有一个演算法，这演算法成功的几率是 p，就是说它比 p 就比如说 p 是1/3嘛，但想要看看 run 3次会成功一次，感觉是这样。那所以说你要让这个演算法非常容易成功，大概就是要让一除以 p 那么多次。你要可以想象，如果 p 是1/6的话，大概就是6。比如说一个骰子，如果你要骰到一个正面的话，你要骰到一个数字是1的话，大概要骰6次，就是大概1除以 p。那或者是说法就是说，你只要做大概1除以 p 这么多次，就可以让至少一次成功，对，这里把 约close。OK， 那换作刚刚那个一开始那个 Guavers 那黑盒子，他是说 ，if I have 我有一个盒子，它里面有一个 solution，对，我随便抽一个，假如我给你一个算法，就是说我随便抽一个，那这个算法成功的机会是1除大 N 嘛，对，所以我大概要让大 N 次才可以得到正确答案，这是非常直觉。Okay, but since we have Guavers, so these Guavers algorithms tell you that indeed if you have successful rate p, then you can use Guavers algorithm to run on you can make this classical algorithm as an oracle and use Guavers to run it. Then you get a square root of p. So indeed you get 1 over square root of p times. 也就是说你有个开根号的加速，对吧？你有开根号的加速。那so the proofs so the idea is that suppose your original algorithm A will success with probability P. So you can think that after you run this algorithm will success with you get some state with the square root of P1 plus square root of 1 minus P0. So this means that you get answer 1 with probability P. 你可以想象就是这个 state， 你 run 完这个 algorithm 然后这个 algorithm 它变生成一个 state， 大概长这样。Okay, but you can use a Guavers algorithm and make a rotation on it, right? Then you get a result is 1 over square root of p times. So remember that the previous example is p is 1 over square root of 2 to the n. But you can use this Guavers algorithm to do rotation, and you only need 1 over square root of p times. So this is the proof exactly the same. You just imagine this is answer state and the wrong state, and you use a rotation. OK，这大家记住了啊！我再讲一次，就你有一个演算法，它成功率如果是 p 的话，对不对？那你应该要一除以 p 这么多时间来让它得到正确答案。但是如果你有 Guavers 的话，你只要1除以根号 p 这样。OK， 那正法就跟刚刚的一样，就是你把它想成是 vector， 那就是 rotate， 所以你可以 square 的boost。哎，如果你被说服的话，那等一下可以看这个 example。这 example 又更难讲清楚，就是比较复杂，大家可以稍微这没听过也可以听一下，可能一开始比较不会听。This is called element extended。这个意思是蛮明显。So idea is that I give you a function f, and the goal for you is to tell me that this f is 1 to 1. That's it. So I give you a function and tell me f is 1 to 1。这意思说我给你个 f， 你要告诉我这个 f 是不是1对1的，或者是你可以这样想，我给你一个盒子，这个盒子里面有很多不同颜色的球，我要知道这个盒子里面是不是所有的球都是不一样颜色。OK， 所以这个是 very difficult question. Right? If you run classically, there's no way you can do. You just need the only way you can do is do it one by one. 我给你个箱子里面那些球，对吧？我问你球的里面的颜色是不一样的，全部是不一样的，那你只能一个一个拿出来看啊，对不对？除非其中只有2个是一样。Okay, so the question for the classical lower bound is n, right? There's no way that you can do better. 那 quantum 怎么做呢？这有点复杂。我讲一次而已。如果 听不懂，下课再问。Okay, so idea is that you first figure it out. You do the same thing, right? As previously, you figure it out randomly and store it as best you got. 你选 L 对不对 ？L 看。Now you say that if I have and you now you can run a classical algorithm. This very algorithm is actually n minus rest n minus L to see if there's a collision. But now it's different from the previous one. Previous one, since I say that if f is equal to 1, right, then there will be L solutions between the n minus L and f. But now since I don't give you any information on f, so if there's if f is not injected, then there will be one solution. There will be one solution of the rest of square n minus L and f. But this is not the case, right? Because the reason is that there may be n minus 1 L. There may be maybe the collision or the set element looks as in split interior. Then there will be no solution. 哎，我要跟我讲，就是说，这个问题是你像有个箱子，这个箱子里面呢有两颗球，可能有两颗球是一样颜色。我们先假设有其中两颗球是一样颜色，其他都不一样。那你现在先抓 L 个球出来，对。这 L 个球如果你抓 L 个球，有其中两个是一样颜色，那你就成功了，但是几率很低。那我们现在想要你抓 L 个球都是不同颜色，那你把它丢在另外的地方，然后变成一个 table，等下去查。那剩下来的 n 减 L 个球里面，有没有可能就真的有一颗球跟你 L 抓出来是一样颜色？不一定，对不对？因为有可能你一开始抓出来这个 L 颗球里面根本就没有一开始是两个颜色的那个颜色。大家搞清楚。我画maybe here 对吧？你要有一个箱子嘛，有很多不同颜色的球，其中两个球是一样颜色，比如说这一个跟这一个是一样颜色。OK， 那你现在执行这个演算法，你先把 L 个球，你先随便看 L 个球，所以这边现在抓了 L 个球，然后你的算法就是说，我有 L 个球在这里，我就去查剩下的这个箱子里面。是不是有一颗球跟这里是一样颜色的？如果有，我就成功了。可是这有一个情况，对，最好情况是这样，这一颗球，有一个绿色的球，一样颜色的球被你抓在这里。OK， 那么你查剩下来的机会，只会有一个正确答案 match 到它。但如果运气不好的时候，你一开始抓到这个球根本就没有在这里，那绿色球在这里，然后剩下的这些全部球都是不同颜色，那你去查，那你就查不到，因为你放在 table 里面只有个 L 的球，可是 L 的球里面根本没有任何一个跟这里是一样颜色。那这个算法的成功率多少？大家知道？慢慢讲一下。这个算法成功率是不是 L 除上大 N？So this algorithm has success probability L 除上大 N。因为如果说这个 algorithm 要成功的话，就表示你一开始抓出来这 L 的球，你要有一个是重复颜色，你一定要查在哪？比如这个绿色必须要跑在这里。你才会查到它。假如没查到的话，所以你一开始选出来这 L 个里面当中要有一个人是正确的家伙，那这个几率是 L 最大的。对，要说你现在这个盒子里面有一个秘密的球是绿色的，那你随便抓 L 个，那要抓到这个 L 的就是要 L 最大的。对。OK，so，听懂了。OK，好，那这样好了，假设你现在使用刚刚这个算法。So the number of times， 你现在使用刚刚的算法，你先找 L 个，对吧？然后你剩下来的 n 减 L 个，你用 progress 去查。那运气最好的时候有一个 solution， 所以是 square root of n minus。If there's no solution， 那你也是 square root 这个。所以你现在有一个算法，它用了一个 guaver， 是 L 加上 square root n minus guaver and the success probability 是 L 除上大 N。那么对吧？所以我先用 guavers， 我先用这个答案，可是我还没有得到正确答案，那我接下来怎么办？我再用第二层 guaver， 我把这一个 guaver 这一个算法包在用第二个 guaver 把它包住，所以我让两层 guaver 算法。那第二个 guaver 算法的成功率就是反过来的，所以你刚刚有讲，成功率是 L 除上 n 的话，你只需要反过来 ，square root of n minus 1 L times 就可以 make 这个 algorithm success probability 1 close to 1。 OK，所以结论是这样，就是这个 algorithm success with L so the number of times is L by square root of minus one L times square root n divided by 就是这样，就是说这个你现在写到这里，对吧？那你用第二个瓜尾去把这个瓜尾包住，所以你最后总共花的次数是 L 加上根号 n 减 L，这是你每一次花的时间嘛？那 you times the number of one divided by square root of p，对不对？所以是这样子，n 除上 n。Now if you pick, now it's the same tree, right？你现在选 L 是 n 的三分之一，那么这一个就是 n 的三分之一加 n 的三分之一了，对，对，还是 n 的三分之一嘛，大概。那这个是 n 的 n 除上 n 的三分之一，n 的三分之一的开根号还是 n 的三分之一。So total algorithm n 除了 two divided by， 哎，哎，对吧？这样就比那个稍微要小，多少？应该是对，我哦，因为我这边是 n 的三分之一嘛，那这个是根号 n 减，对，我看一下，对，呃，this expression. So I pick L to be let's say n 哎，另外哦，如果我选 L 是n 的二分之一，那这个就是 n 的二分之一加上 n 的就二分之一，就是这个这两个相减，就是二分之一开根号四分之一，i 的就是 n 的四分之一。对，你现在如果 n 是n 的二分之一的话，就是 n 的二分之一。那这个是根号 n 减掉 n 的二分之一，就 n 的再开到4，然后就乘上是 n 除上二分之一再开到24。Right, so this algorithm will make success 4 divided，因为这个就没有，就 n 的二分之一加 n 的四分之一还是 n 的二分之一，所以你要 n 的四分之三次方啊。诶，那 n 的两项均之后会比较小。哎，对，待会帮你画。所以after you pick L to be square root of n, then total times n to the 0.75。你先想一下这件事发生什么事？这说如果你有集合，对不对？这个集合里面有 n 个不同的球，n 个可能有重复颜色的球，你其实只需要 n 的0.75次方就可以把整个集合看完，发现它有没有是不是一对一。这是一件非常奇怪的事情。你有一个方选，它是不是一对一？可是你要判断它是不是一对一，可是你没有把它，你现在没有把它全部看完，你只看了 n 的0.75次方。OK，所以这就是这个 algorithm 神奇的地方。那很神奇的地方是，这个并不是最好，这个0.75次方并不是最好。好，刚刚这个错误的计算，对，其实有一个最好的，这没有时间讲，就是说有兴趣的话可以去查一东西叫 common work。说 common work 是可以 provide 另外一个算法是 n 的三分之二次，然后 n 的三分之二次方 of m 的 distinct 是最好。那这个证明，这个 common work 是一个非常复杂的东西，对不对？时间没有什么时间。你就把它想成是一个总人工的算法，然后 Quantum 可以比 Classical 有更高的机会，可以走完这个迷宫这样，听起来很爽。Okay, so this is called M distinctness and probability. So the number of is 3 divided. Oh, so we have like three different, right? Three different. Problem one is unstructured search, which will take us further in. And collision that which is better than collision is like 1/3, and element distance is 0.75。这个 Power algorithm 可以做到一些你原来想象不到的事情。那我们第四个问题是这个等下下一堂的这个叫 parity。parity 比较神奇，就我要知道，我现在要知道我给你一个盒子，对不对？里面有黑色跟白色的球，我要知道黑色的是不是，我要知道黑色是不是奇数，对吧？这要奇数还是偶数？所以这个问题更难。这个问题是说我换一个我要知道正确答案是奇数的还是偶数，这叫做 parity。那这有没有量子加速？好，我们下一堂课来讲，对吧？好，有问题要前面问，休息。